Hello everyone. Thank you for taking the time out to listen to this presentation. My name is Danielle Nordajali, and I am presenting on a paper entitled Estimates of the Neutron Emission During Large Solar Flares in the Rising and Maximum Period of Solar Cycle 24. Let's begin with what are solar flares? We've all heard of them, but I'm sure only a small handful of us fully understand what a solar flare actually entails. A flare is a sudden, rapid, and intense variation in brightness. Magnetic energy builds up in the solar atmosphere and is suddenly released. As the magnetic energy is being released, particles are heated and accelerated in the solar atmosphere. Different wavelengths of light are emitted at this point in time, all throughout the electromagnetic spectrum. A varying amount of energy can be released and is scaled accordingly. Solar flares are classified as A class, B class, C class, M class, and X class, from smallest to largest. Each classification is a tenfold difference from the prior classification, and within each classification is a finer scale 1 through 9. However, X class can exceed 9 in scaling. Solar flares can emit up to 10 to the 32nd ergs of energy. In terms of joules, that is 10 to the 22nd kilojoules. In comparison, that is 10 million times the energy released from a volcanic explosion, but that's less than a tenth of the energy released from the sun every single second of every day. Now, the sun we all know and love goes through what are called solar cycles. To give you a relative idea, it's like a sine or cosine graph, just not as evenly distributed. In other words, it has a minimum, it has a maximum, and when it returns to the minimum again, it's a new cycle. In the release of particles from a solar flare, ions can interact with the solar atmosphere and create secondary neutrons. These secondary neutrons can go from the sun directly to the Earth without being affected by the interplanetary magnetic fields. Remember those wavelengths of light I mentioned earlier? Well, they reach the Earth much faster than the secondary neutrons do, and the X-rays are a good indicator of just how intense the solar flare was. In this experiment, the X-rays were observed by geostationary operational environmental satellites, which record every minute. Most of the time, the secondary neutrons are scattered or absorbed once they enter the Earth's atmosphere, so they are rarely detected by the satellites. So there is an assumption that every time X-rays and gamma rays are released from the sun, the secondary neutrons are released as well. Most measuring techniques of the secondary neutron are by a neutron monitor, but in order to detect both the X-rays and the neutrons, the scientists use solar neutron telescopes as well. Across many different years, the efficiency of the solar neutron telescopes were tested using a Monte Carlo simulation against the efficiency of the neutron monitor. Here, you'll see in purple is a reading efficiency of a neutron monitor over different kinetic energy levels. The other markers on this chart are different locations of the solar neutron telescopes, the locations indicated by their names, their minimum kinetic energy reading value, and their efficiency on being able to detect the incoming secondary neutrons distributed evenly across the detector at a vertical injection angle in their three possible settings: neutral, neutral and charged, and directional. This study took place from January 2010 to December 2014, and through this time, the geostationary operational environmental satellites detected 43 solar flares greater than X1.0 class. They did, however, have to discard some of this data because the solar flares weren't able to be vertically incident with a satellite in Japan, and another satellite listed in the study was run independently. So here you'll just see a list of each solar flare detected and by which solar neutron telescope, along with their ranking on the solar flare intensity scale. Next to this chart, I did provide a legend for the solar neutron telescope names. Here, we have 4 different count rate profiles from the solar neutron telescopes, 2 of which were the highest recorded intensities. So in the upper left corner, we have a reading of the X6.9 class solar flare from the telescope in Gornergrat, Switzerland. Upper right is Yangbajing, China. Lower left is Mauna Kea in the USA and Hawaii. And lower right is Mount Chacaltaya in Bolivia. The readings on the x-axis are in universal time based on the Earth's rotation, and the y-axis is a calculated deviation of each 2-minute count of the data. The scientists set a work window of plus or minus 3 hours from peak time, which is the time at which the maximum intensity of the soft X-ray flux was examined by the geostationary operational environmental satellites. They then took that time frame and broke it up into intervals. The first was for the backgrounds and possible excess from the secondary neutrons, and the second was specifically for the neutrons. Within the hour highlighted in purple is the signal window, in which neutrons can be produced simultaneously as the X-rays. Each flare's peak time is shown using the dashed blue line, and the red line is the average background. Next, compares the same 4 satellite readings in a different kind of chart. So the background distribution is the blue outline, the signal distribution is the shaded in bars, and the red line is a Gaussian fit to the background distribution. The significance was calculated using the deviation of each 2-minute count from the data on the previous slide and normalizing that by the Poisson standard deviation for 2-minute counts. Then, the data distribution was fit to a Gaussian function. So to evaluate these figures, they considered anything greater than plus 3 significant figures as a candidate for a solar neutron event associated with a solar flare. They then analyzed different reading levels on one solar neutron telescope, the one from Gornergrat, Switzerland. On the previous slide, they compared the 4 megaelectron-volt readings of different solar telescopes. On this one, it compares the 40 megaelectron-volt readings to the 80, 120, and 160 megaelectron-volt readings, since this solar flare was the most intense reading during the solar cycle 24. By analysis of these diagrams, you'll notice that there is little to no data past the 3 significant figures for any reading, meaning that the data presented here does not contain solar neutron signals. So, since our data set didn't contain solar neutron signals, they had to estimate the upper limit of solar neutron emission based on the assumption that when a solar flare occurs, solar neutrons are produced at the same time as the soft X-rays are. In order to calculate that, they took the detection threshold of solar neutrons as 3 sigma over the background. With consideration of fluctuation of signal plus background, the upper limit is a value that gives less than the threshold within 90% confidence of signal plus background. All of these considerations allow the scientists to estimate the neutron emission at the Sun. They assume the energy spectrum of neutrons at the Sun using this equation, where C is the neutron emission at energy of 100 megaelectron volts. Beta is the differential power law index. Next, they consider that neutrons traveling into interplanetary space will decay, so the equation was changed like so. Omega is the solid angle given by the solar neutron telescope area divided by 4 pi times the concentration of the astronomical unit squared. P of E is the neutron survival probability against decay. This equation was further modified after accounting for the neutron's attenuation in the atmosphere. This value was calculated solely using the data from another paper of the nuclear interaction model of Shibata. On the table shown are the estimated values of neutron emission from the Sun at each solar flare using the equation they created. They compared the calculation values with calculations done during solar cycle 23, and they concluded that their values are consistent with those. They used Forrest and Choupe's balloon experiment from 1967, which had no positive detection of neutron emission, which estimated the solar neutron flux in the energy interval of 20 to 120 megaelectron volts to be roughly 0.002 per centimeter squared seconds. They used Kirsch's data using the neutron monitors in Bolivia, Argentina, France, and Switzerland, which also had no positive detection. But he estimated the upper limit for solar neutrons using the Schree method of epoch superposition. When comparing 2 time series using this method, you have to begin by defining each occurrence of an event in one data sequence, series 1, as a key time. Then, you have to extract subsets of data from the other sequence, series 2, within some time range near each key time. Lastly, you have to superpose all extracted subsets from series 2 with key times for all subsets synchronized by adding them. The third scientist's work they used was Sukiya's upper limit calculation from the China neutron monitor in the rising period of solar cycle 23. They ended up calculating 4 upper limits in different time zones, and they are as follows: 0.01 ergs per steradian, 0.001 ergs per steradian, 0.0001 ergs per steradian, and 0.00001 ergs per steradian. And each zone had the data as follows. Zone 1 had 7 upper limits events, which was 20% of the data with no successful detections of solar neutron signals. Zone 2 had 16 upper limit events, which was 45.7% of the data with 1 successful detection of solar neutron signals. Zone 3 had 12 upper limit events, which was 34.3% of the data with 3 successful detections of solar neutron signals, and Zone 4 had no upper limit events with 2 successful detections of solar neutron signals. Their conclusions from the data were 1. The neutron energy may not exceed 0.1% of the soft X-ray energy. 2. Most solar flares are concentrated with the energy of the solar neutron events divided by the energy of the soft X-rays between 0.001 and 0.0001. But is not in association with solar neutron production. And third, the probability of solar neutron detection as a function of fractional neutron energy can be obtained because of the necessity of an upper limit calculation of the previous solar cycle. And that concludes my presentation. Thanks again for taking the time to listen and watch. I really hope you enjoyed this presentation, but if there are any questions, comments, or concerns, you can leave them here at the bottom in the comment section, or you can follow up with my email address provided in the description of the video.